Do you hear me? Hello? Excellent. Good morning, everyone. So just a word about CSEM. CSEM is a research and technology organization spread over Switzerland and whose primary mission is to transfer technology from academics to the industry by raising TRL over foolhardy projects. And my group, as mentioned by the chairman, Smart Connected System, is doing IoT since before IoT was coined. And now our specialty is to handle IoT when it is not foreseen possible by the customer using what is available on the market. And many people here, brilliant people, are making my work very hard, because when I see what is done, it's difficult to go beyond. So we have now to address sustainability as a requirement, for sure, because of the global situation. And there is one good news when we think about IoT and sustainability, is that IoT is part of the solution. I mean, you have heard speakers this morning. You understand that if we can sense everything, everywhere, everywhen, I mean, we get better control of processes. So we can optimize. We can optimize a lot and save resources, energy, materials, goods. So definitely IoT is here to stay in a sustainable context. Now it comes with its own cost, with its own footprint. I mean, we used to tell a lot to people 10 last years, yeah, we will deploy billions of sensors everywhere. Yes, but what's the impact on the environment of those sensors? And this is what we try to address now together with our partners. So I'm here to speak about pathfinding this sustainable electronics. We are speaking about small systems, small remote sensors, but also light computer peripherals or wearables. It's a bit broader. And what we have to start with is the life cycle analysis. Most of you already heard about, but you need to get a good quantification about what's happening to your product, not just when you dispose it. I mean, what do you need as materials? How do you process them? What is the real cost of your product during the whole life cycle? And then you get a clear view about where you can start to act to change things. I mean, recycling, you already all know about recycling materials, but it has to be orchestrated. You can remanufacture. So in some cases, even the components do not need to go back as a material and be remanufactured, but you can reuse components to remanufacture. You can also reuse the devices, definitely, for the same purpose, or perhaps reprogram them for another purpose. And finally, when you have activated all these areas, you have to dispose what rests. And you have to take care about this disposal. I mean, hopefully you incinerate it, not landfill, because this is the worst approach. And incineration, like I've asked one of our speakers today, you need not to have toxic waste, but as well be neutral in CO2. When you have system you cannot recover from the emission, then you have to start handling biodegradation or composting to ensure that it will not be a bad heritage for future generation. All of this is changing design for sure. This is a bit engineering. And this is not the only thing. I mean, things are changing now because there is a societal evolution. Consumers are sensitive more and more to environmental concerns, but also to their wallet. And we are in an environment where resources are declining. Definitely, strategic metals, everything, oil. So it will drive also a change in the design, especially in the feature set. Will you go for nice to have or minimalist feature set because you do the mission and this is what you pay for and this is what has the minimal impact on the environment. So prepare yourself to change the way you devise products and also their business environment, their economical footprint. So this is where we operate. Now you have understood that we have to do design rethinking, we have three main approaches in the group, which is design for disposal, design for disassembly, and design for longevity. Let me explain that. If you take very short-lived product, or short-lived, I mean, this is product you activate, you use, and this is finished. The environmental footprint is mostly in production and end of life. The use is pretty short. And in this kind of application, I put here RFID, but we try to make something more than RFID nowadays with sensing, etc. You see on the bottom a bioassay that is for a condition. So you test in urine or saliva, and it connects directly to your mobile phone and tell the results, and it can be a complicated analysis. So you need silicone there. But the rest, we try to reduce materials, to use biosourced materials, and depending on the mission of the product, to use biodegradable or at least incineration-friendly materials, and at least something inert. Hopefully, silicone is something you can eat a chip a day for your entire life without having a health concern. The rest has to be exchanged when you cannot put in your chip by sustainable counterparts. And we work on that. Firefly is a system on chip we are now developing. And we have new challenges. I mean, there are many systems on chip on the market now doing sensor interfacing, communication, local computing, etc. But when you get all around sustainable components, they are not from DigiKey. I mean, they have very strange behaviors when they are made out of these materials. And we have to make the silicon you see here capable to handle these external components, to finally have something like a grain of sand in a cradle of sustainable components. Another approach, design for disassembly, that we do not already apply that much, but we try to bootstrap, is to concentrate and separate things you can recover and those you can't. But already in the product at design, you know that today products are very intricate. So when you have to disassemble, when you have to separate, it's very complex. So making them separable is a mission. And we are helped by the industry because simply about profits. I mean, look at a computer keyboard here on the top. This is a high-end keyboard. You have a PCB on top, and this is a lot of oil, polymer, strategic metals, etc. Now look at the low-end counterpart on the bottom. See the change? The complexity is concentrated on the top right green stuff, which is a small PCB, easy to detach, to separate. The rest is a PET membrane with a carbon ink. We don't see that all products can go the same way, but this is done for cost reason. Now imagine that we replace PET by a biosourced plastic. If you incinerate, you are carbon neutral. So you can make small increments that are very important in terms of impact, and you can hook this to the actual production process. A third approach is design for longevity. Why? Because the mission of some products is very long. And I take as an example here retrofit sensing in big construction. You have also monitoring of the land for catastrophe prevention. Retrofit building monitoring. I mean, the mission, it's like 8 to 10, sometimes 15 years or more. I've seen speaker being even more competitive than that. And here, the use dominates the environmental footprint, not the production of end of life. So we have to go for ultra low power, but beyond standards. And this is where CSEM is a good actor in microelectronics. Not only about standards, but also going for new technologies and new kind of topologies, but also energy harvesting. This has been mentioned this morning. Definitely, many people are doing harvesting. Now we see a new trend because we have customer coming and we see, yes, we can do some light harvesting or get the temperature or vibration. Problem is the determinism. Some of our customers say, no, we can't bear with that. We are in the basement. There is no light. We are not sure there are any vibration. We need to operate deterministically. And this is where we enter the game with wireless power transfer, because then it is deterministic. It is still without a wire. We have still no or very little battery, but then you are sure about the power. So all in all, the way we work is to have industrial partners, and we analyze their product. Often this kind of partner have already made a very extensive analysis of their product. And we propose sustainable alternatives coming from CSEM, from other RTOs or academics. And we assess, we quantify the benefits sustainably, because these people are very allergic to greenwashing. It must have an impact. Then we assess the TRL. This is what we call foolhardy projects. And we do prototype integration. Finally, before delivering solution portfolio to the customer, we have to get IP clearance, at least freedom to operate, or a bunch of licenses whose cost will not be an impediment to commercialization. In short, a takeaway is that there is no single solution for sustainable electronics. It is mission dependent. We need to build up portfolios. We need a quite broad scientific exploration. CSEM is not so big. So we have a big research network and European projects, Swiss projects. And finally, we need a good industrial partnering so we can focus on real products and find the right solution. So my conclusion is that I invite industrial to join us to put their solution under sustainable steroids. Thank you.